Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit. Today we're going to be talking about the AIME-GM-HM inequality and along the way reviewing the different means, the arithmetic mean, geometric mean, and harmonic mean. Let's start with a quick review of these. You can check in the comments and description below for links to the old videos we did. We did one on the harmonic mean before. We have one describing the AIME-GM inequality by itself. But let's review quick these different means in detail. First one is the arithmetic mean, or AM, of n numbers. This is your normal average. You add up all the numbers a1 up to an and you divide by n in this case. So this is the normal one we talk about or think of when you hear the word mean. There's also, however, the geometric mean. So where the arithmetic mean is with adding, right? Arithmetic adding, arithmetic sequence, geometric mean multiply. So instead of adding and dividing by n, we multiply everything out and take the nth root in that case. Last one, harmonic mean, HM, is harmonic here. You can think of harmonic series, which is the series 1 over n, things like that. It's reciprocal. So we have n divided by the reciprocals of all of the numbers there. So this looks a little bit like the arithmetic's mean, except it's flipped and kind of the AIs are all flipped that way as well. So let's look at this first with a quick calculation and a quick example of these here. So we have our three different means, our arithmetic mean, geometric mean, and harmonic mean there. And let's suppose we have three numbers, 1, 3, and 9, and we want to calculate the different means in each of these cases there. And as a little bit of a preview, let's try to compare them a little bit too in terms of their values as well. So arithmetic mean, this is the normal straightforward one, 1 plus 3 plus 9 divided by 3. So here we have 13 over 3, so that is our number as a fraction there. And right, this is going to be 4 point something in that case. Comparing this to the geometric mean, remember this one we already know is less than or equal to the arithmetic mean. But let's see it in practice. We have the cubed root of the product of these numbers. So 1 times 3 times 9. This one can normally be pretty messy, but right, we have nice numbers here. 1 times 3 times 9 is 27. Cubed root of that is, of course, 3. So we have cubed root of 27, which is 3 here. For the harmonic mean, remember now this is like the arithmetic mean, except a bunch of things are flipped around. So we have 3 over 1 over 1 plus 1 over 3 plus 1 over 9. So here we have, this one takes a little bit more simplifying, so let's do it in 2 steps. We have 9 ninths plus 3 ninths plus 1 ninth, so we have 3 over 13 ninths here. And so this is going to be 27 over 13 in this case. So it's not too hard to see here, at least in this example, that the arithmetic mean is 4 point something, 4.3 repeating is bigger than the geometric mean, is bigger than the harmonic mean, right, which is like 2 1/13 there. So we have a little bit of a preview of the different values in this case too. Now, we've seen harmonic mean before in the previous Thursday tidbit linked below, but let's revisit that and compare the arithmetic mean and harmonic mean with rates and speeds and things like that there. So Mark drives for 1 hour at 60 miles per hour and another hour at 60 miles per hour, sorry, 40 miles per hour and 60 miles per hour here. And I want to highlight here that it's 1 hour and then another hour in this case. So how would we calculate his average speed? Right, his average speed is always going to be the distance divided by the time, right? That's always how we calculate the average speed. So distance, there's a little calculation to do here, right? So the average speed is, okay, the distance, well, he goes 40 miles per hour, 1 hour, so that's 40 miles. He goes 60 miles per hour for another hour, that's 60 miles there. And then the total time is 2 hours there. So this is going to be 50, but I also want to point out here that note our calculation here is the arithmetic mean in this case. So we have the 240 plus 60 divided by 2 if he's going the same time for each rate. We can find the average by doing the arithmetic mean. Now let's look at a similar, very similar, same numbers of course, except now James is driving 60 miles at 40 miles per hour and another 60 miles at 60 miles per hour. What is his average speed in this case? Well, let's do the same initial formula, right? We find the total distance divided by the total time in this case. Now here the total distance is 60 plus 60, so 120 miles. And just for illustrating the point here, let's kind of unsimplify or keep the denominator of the time unsimplified here. So if he goes 60 miles at 40 miles per hour, that takes him 1.5 hours because we have 60 divided by 40. And then it takes him 1 hour because it's 60 divided by 60 to go 60 miles at a rate of 60 miles per hour. Now the reason I wanted to leave this unsimplified is that if we cancel all of the 60s, we have 1 plus 1, so we have 2, and then this is divided by 1 over 40 plus 1 over 60 in this case. Right, this isn't the easiest way to simplify this. If we were just coming up with the original answer, right, you could do 120 divided by 2.5 in this case, right, because you have 1.5 plus 1, right? So regardless of how you calculate this, you are going to get 48 miles per hour as his average speed here. But I just want to leave it unsimplified that way because it's clear in this regard that we have the harmonic mean in this case. So comparing our two speeds, we have arithmetic mean is 50 miles per hour and the harmonic mean is 48 miles per hour. And again, we can kind of see that the arithmetic mean is higher, larger than the harmonic mean here. And that one makes a little bit more sense intuitively in this type of problem. Because if you're going the same time on both speeds, right, then you just find the arithmetic mean, the average. But if you're going the same distance, that means you're going a longer time at the slower speed, right? A slower speed means a longer time, and that's why this average is a little bit smaller. That's why that average speed is smaller in this case there. So arithmetic mean, harmonic mean don't play super well together, or they play well together with rates. Geometric mean not as much, but let's look at a different example that involves the geometric mean and then we'll relate it to the harmonic mean and arithmetic mean to end as well. So let's look here at a geometric example. Again, let's look at our 40 and 60. So we have a semicircle and it has a diameter of 100 and we're drawing this perpendicular line here that divides this diameter into lengths of 40 and 60 in this scenario. And we want to find out how long this line is. We want to find the length, let's call this m, of this line in this scenario. So we have a diameter. Now, if you know a little bit about your circles and your angles and stuff, right, we can think about, okay, what happens if we draw a triangle that has a hypotenuse of this diameter? Well, if you know your circles and arcs and angles, this is actually another right angle there. So this actually says, right, since we have a semicircle, since we have a diameter in this case, we have actually three similar triangles in this case. This blue triangle, the whole triangle here, right, it's a right triangle. We have two angles there. Then that triangle is going to be similar to this triangle right here in orange, and it's also going to be similar to this triangle here in pink. All right, so we definitely have these similar triangles in this scenario there. So our kind of key observation for this problem to get started here is we have these similar triangles that we can work with. Now, right, what does that tell us about these distances and these lengths involved? Well, right, let's look at the orange and the pink triangles in this case. Okay, they're one side compared to the other. They're two legs. So we don't know the two hypotenuses there, right? We don't know the legs of this blue triangle. But we do know the legs, at least in terms of the variable m, for the pink and the orange triangle. So the ratio of those sides, let's say m divided by 40, that is equal to, well, on the other side, these legs are flipped. So we have 60 divided by m. And so pretty quickly here, we have m squared is equal to 40 times 60. And just leaving it unsimplified a second, we see that we have our geometric mean. We have two numbers here, so it's just the square root of the product of those numbers in this case there. So m is the square root of 40 times 60. And right, if you do this, you can simplify this to 20 square root of 6. Those of you paying attention or want to know your decimals and numbers a little bit, this is 48.99 approximately. So spoilers again, this is less than the arithmetic mean, but actually bigger than the harmonic mean as well. And let's use this same picture to prove, at least for two numbers, x and y, that we have this relationship between the arithmetic mean, geometric mean, and harmonic mean. But before we kind of jump, just to review this one, because we'll see it again, when we have this semicircle, we have a length x, length y. This perpendicular line is the geometric mean there. So if we look at the general picture here again, let's kind of really quickly label that geometric mean right here as square root of x, y. So in general, it is the square root of x, y. It is the geometric mean is the length of this perpendicular line we have here. Now, as soon as we see diameter x plus y, that should get us into thinking about, well, a radius. A radius is x plus y over 2. So if we look at the center of this circle, if we draw our radius in here, then of course this radius has a length, right? This total length here of our radius is going to be x plus y in this case over 2. So our average of x plus y over 2 in this scenario. Now, just summarizing these, this is kind of pretty easy to start here. Notice we have a right triangle. That right triangle has a hypotenuse of x plus y over 2. which I just want to point out is our arithmetic mean of the two numbers x and y. And that hypotenuse, of course, is at least as long as the leg, which is the geometric mean square root of x plus y. So this is our geometric mean there. And we know for sure that this arithmetic mean is bigger than in this picture of where x is not equal to y. So we have this diagram. We have this is bigger than the geometric mean in this case. So that is our setup of these to begin with there. Now, things are a little bit tricky for the harmonic mean. This is a little bit harder to look at, so let's practice our similar triangles again. This is going to be a picture that's going to be similar to the previous slide, except kind of happening inside of this shape here as well. So let me kind of put a question mark on this length right here. So this hypotenuse, or not hypotenuse, this leg of this triangle here, let's call this variable z in this case. So that is our kind of z length there. So we have our full radius of length x plus y over 2, and then this z value is the leg of this smaller right triangle that we have here. So we have this right triangle like this that we are comparing as well. Now that right triangle is of course similar to the bigger right triangle that it lives in, right? This bigger right triangle that had the hypotenuse of the arithmetic mean and the leg of the geometric mean in that scenario. So if we look at those two similar triangles there again, so we're still taking advantage of these similar triangles. The leg, so let's look at the smaller triangle first. This leg z compared to the hypotenuse, square root of x plus y. That is the smaller red triangle. Now that is similar to the bigger triangle where now the leg is square root of x plus y, right? This is very reminiscent of the previous slide, but now we have our arithmetic mean in the denominator there. So this tells us about z. So if we solve for z, we have this is xy, so square root of xy times square root of xy over x plus y over 2. Now a little rearrangement gives us that this 2 comes on top, and then we can divide by xy in this case. So if you do a little manipulation of this, we get 2 over 1 over x plus 1 over y. And lo and behold, right, that is our harmonic mean in this case. So, right, since we have z written like this at the bottom, let me just write here, it is greater than z, which is the harmonic mean in this case. So we have our three means all expressed in this diagram here, in this semicircle and perpendicular lines. The radius arithmetic mean is greater than this square root of x plus y, which is this perpendicular line, is greater than a portion of that radius, which is the harmonic mean 2 over 1 over x plus 1 over y there. If you think about this a little bit, you'll actually get that these three things are equal if x equals y. So if we divided this in half anyway, the geometric mean is also a radius, and then this perpendicular line, kind of z, the harmonic mean becomes the radius as well, so everything is the same in that case. So just to clean up and finish, let's look at the total AMGM-HM inequality. So for non-negative numbers like this, just being more formal in this case, the arithmetic mean, so we add up all of the numbers and we divide by n. So we start with our arithmetic mean is greater than or equal to the geometric mean, so that is the square root of the product of all of those numbers, is greater than or equal to the harmonic mean in this case. And we do have equality if and only if all the numbers are equal. So you can do some inequality problems with this, right? Look at that AMGM video for one example of those. But it's also just good to think about the different means and their different applications as well. Thank you guys for watching this video. Check back each Thursday for a new math tidbit. And I always want to recommend ZIML.areteem.org for more practice, more resources, great things there as well. And be sure you like and subscribe to this video if you enjoyed it as well. Really helps us out there too. Goodbye, everyone.